Hello, everyone, and welcome back to Statics. We've been talking about trusses the last week or so, and remember that we were looking at things, maybe simple truss like this, whole bunch of members, whole bunch of joints like this, and then some support reactions. So let's say a roller over here and a hinge over here, something like that, right? Maybe a load here and a load there, whatever it is, right? And so we went through and we found two different ways to find all the member forces, or at least some of the member forces. So we used the method of joints, where we just broke everything apart and did a whole bunch of particle equilibrium free body diagrams, or we said, like, we can break it apart. Of course, this one wouldn't work. I'm missing a cross beam, just like we did in class. We missed it. Right, so I could cut across here and just find those. That's what we call the method of sections. So we did both of those. Now, one of the things that was very important about trusses was that the forces only acted at the joints. Right? And that was important because if the forces only act at joints, then we know that all members are, that's just two, number two, it's easier, two force members, right? That was special about the trusses. Now, what we're going to talk about today is a frame, which is similar to a truss, that it has a bunch of members that are connected by pins or by joints. But now the load can be anywhere, right? It doesn't have to be at the joints. And we're going to talk about two different ones. We're going to talk about frames that are collapsible, and then we're going to talk about ones that are non-collapsible. What do we mean by collapsible and non-collapsible? Let's think about something that looks like this. Very simple frame. We have a member here, and then there's a connector at the top, some pin or something, and then we have a hinge here and a hinge there. All right, that would be my frame. Let's put some loads on there, and there. All right, something looks pretty straightforward. Now, the reason why we call this collapsible is that if we take away just um, a single support reaction, then our system is going to deform. Right? So if I think about the same setup, like this, and like that, I still have my hinge over here, but now I take away one of the support reactions. I take away the support reaction in the horizontal direction, right? Then I would have basically a roller over here. I still have my two loads there and there, right? Then we know that this whole thing is going to start moving away, right? So the overall shape wouldn't stay the same. It would start collapsing, and I would have something, basically flattens out or goes all the way down, whatever it is, right? But it's definitely not going to stay that same shape. So that's what we call collapsible. And then if we have something that's non-collapsible, let's do another one over here, right? If I have something that looks like this, maybe, right, where I have one joint from here to here, and then I have another member. I mean, so a member from all the way up there, and then a member all the way down here. Say I have a hinge here and a roller there, right? And then let's put a load on there, make it useful, right? So again, this is just some kind of structure that's holding up a load. Now, if I take away this one, like one of the support reactions here, right? So for instance, if I just take away the roller, then, wrong color. Go back to black, right? So I have something like this, and across. And now I don't have that roller there anymore. Joint, pin everywhere. My load, right? So now this whole thing, of course, is going to start rotating in that direction. It's not what we want necessarily, but the overall shape, that kind of, crooked A or whatever you want to call it, right? That shape is going to stay the same. It's not going to change. And that's what we call non-collapsible. And we'll see that what we can do is, if we want to solve these, we approach them slightly different depending if they're collapsible or non-collapsible. And so I think what we'll do is we'll start with the non-collapsible version. Scroll down here a little bit, give us some space. And we'll say 510. Keep on doing the wrong colors, I'm sure. 510. We'll say non-collapsible to L frames. There we go. And so again, we can remove one of the supports and the shape is going to stay. The whole thing might change, move, but the shape itself, the arrangement of the different parts together is going to stay the same. So let's draw something here. Let's make it a little more clear what our members and where they end. So let's do it. We'll do it kind of wider. Let's say we have a bar that goes all the way up here. Should have done a little more of an angle. And then we have another one that goes down, connected by a pin right there. We'll call that point C. And then we have another bar that goes across. And there's a pin that holds it there and a pin that holds it there, right? You can think about these being bars of wood or something. I drill a hole through, I put a bolt through it, a nut, and that's how they're held together, right? So it's 1, 2, 3 different parts that are all held together by what we call pins. And then we'll say we have a support reaction over here. That's a hinge. And we have another support reaction down here. And as usual, that's our roller. We'll have a load sitting at the end. P, so maybe it's kind of like a crane or something. And then let's give some names. So this is A, this is B, we already put C, and we'll put D, and we'll put E. Now we know where all the parts are. And now the question that we usually are asking for frames is, what are the forces in the pins? It's hard for us to kind of give the force, the forces within the members, what they look like, how they change, but we can definitely find what the forces are at the pins. And so what we usually do is we start with entire frame. All right, so what would that look like? Well, that would look like we take this and just create a free body diagram out of that to start. So we have one bar going across, one down, and one down. Just like we did with the when we did the trusses, right? We don't have to care what all the connections are here. We just say it's one big rigid object. We have our load P. We have, of course, all of our names here. So we have A, B, C, D, and E, and then our support reactions. We have a hinge over here. So that's AY and AX. And then here we just have E. And so this would be our free body diagram. So from this, we have 3 equations. We have, I'll start with the unknowns, I guess. Unknowns, we have 3 unknowns and 3 equations. Well, we've done that a couple times, like, how this helps. Our first examples all were kind of a nice flat bar, right? But this is the same thing, right? I could do the sum of moments about point A, that will give me E. I could do the sum of moments about E, that will give me AY, and then AX in this case will be 0 because there's no other force acting in the X direction, right? But this would give me all the forces. all the support reactions I'm showing. Doesn't give me anything about the pins and the forces that are acting in the pins, right? And so what we do for that is we basically take this frame and disassemble it. Similar to what we did with the method of joints, where we like, cut everything apart. Here, instead of cutting the members, we just take the pins apart, right? So I would have, if I look here, right, I would have this one here by itself, that one here, the horizontal one by itself, and then the vertical one by itself, right? And so I can make 3 free body diagrams. All right, I can say I have that one that comes kind of on an angle upward. Let's scroll down a little bit here. So I have something like this. And well, I know I have support reactions from the bottom, right? That's in my top free body diagram. Again, just like with the trusses, we have to make sure that the directions that I have in both of these are the same. But I don't want to have conflicting information about what positive, what negative is. So I have a X and I have a Y. And now I have to take these pins and basically pretend they're just like support reactions, right? So basically I can say my kind of sloped bar right here is being supported at point B and at point C. And so I'll add support reactions there. Also, I have a BX and I have a BY, and then same at C. So I have a CX and a CY. Now I have how many? 4 unknowns. I could write 3 equations, so that's not going to be able to let me to solve this whole thing. But I can do the same for the other 2 parts that I have. I can go to the vertical part here, for instance. Oh, let's do the horizontal one first. Do my horizontal one, put it right there. I know that at the very end of my horizontal part, there's my load P. It doesn't change. But now here I have no support reactions, right? Because I have this bar up here. But now I have my reactions from the pin at B and at D. Now it's very important that when I put these back together, my B's, my BX's, and my BY's, right, have to cancel out. So I have to make sure they're in opposite direction. So my BX here was positive to the right. So in my other component, it has to be positive to the left. My BX was positive upward, it has to be positive downward. BY. And then I have to add more for D. I don't know anything about that yet, so I can say, maybe I'll do another downward one. DY and DX. The ones here in the middle sometimes are a little hard to see, right? So just make sure that we can see what we're drawing. Again, important, BX and BX are in opposite directions. BY and BY are in opposite directions. And then the last one, let's see, what do we have now? Now we have 1, 2, 3, 4, those we already counted, 5, 6 unknowns. So we could solve this because we have 2 and 2. But let's get the other ones in here too, so we can do our last part. No, we could. Let's do our last part here. So we have our support reaction at the bottom. We have E. The top, we have point C. So we have CX and CY. CX was to the right, so now it's to the left. CX was upward, positive for CY, so downward positive. And then DX was downward, DY, I'm sorry, was downward positive. So now we need to have an upward positive. Oops, that's not a C, that's a D. DY, and then it was positive to the right, so now it's positive. DX. Now let's see, we have how many unknowns? We have 1, 2, 3, 4, 5, 6, 7, 8, and 9. Right, so the 2 at each of the 3 joints, and then the 3 support reactions. So now for this system, I have 9 unknowns and 9 equations. Put behind here 3 times 3 equations. right? For each of my free body diagrams here, I can have an equation. X and Y on there. And so I could just go through and solve these all. I can make a mix between the two. I could get A and Y from the main one and then start working on stuff, or I could just go straight up. Yeah, depends on what works better. So that was the non-collapsible frame. So let's see what we do for the collapsible frame. So let's do 511 and call this collapsible frame. Do our simple collapsible frame here. Right there. And right there. Connected by a pin up top here. And then held by a hinge on both sides. And we'll say this is A, this is B, and that's C. And of course, we need some loads. There, it's called P1 and P2, for instance. All right, so this is our setup. Now, if this were a non-collapsible frame, right, then we said like, well, we can go straight in and we just get the overall support reactions. Let's try that here too. Take my overall system. It would look something like this. I have my loads, P1, P2. Again, they're acting now not at the joints, but on a member directly. And then I would have support reactions, two hinges. So I have an AY and an AX. And let's point in the other direction. Oh, this is not B, this is C. So I'd have a CX and a CY. Now, unlike the non-collapsible one, right, where we could solve for them, we can't here because we have 3 equations and 4 unknowns. So in this case, even if we just wanted to get the support reactions, we'd still have to go ahead and break this into its components. So to do that, my left side would just be that 1 bar right there. Let's see, I don't think we can get them all together, so let's just put them down, the 2 down here. So I have 1 right there. Instead, at the bottom, I have my support reactions, AX and AY. Again, important that they're the same in the 2. We have our load, P1. And now, again, we have pin reactions. So we take about this pin. So let's say we have BX to the right and B to the left, to the right, and then BY going upward. And then we can do the other side. We had our support reactions, CY and CX. We have our load, P2. And then, of course, we have our pin reactions here, right? So we just have to make sure that we do them opposite. So BY was upward positive, downward positive, and BX was to the right. So now it goes to the left. So now let's see, what do we have? We have 1, 2, 3, 4, 5, 6 unknowns. We have 6 unknowns. We have 2 equations that we can write. Well, we can even write more. We can do 9 equations, but we could just do 6. But let's write down. We have 9 equations. And 6 no, so sure we can definitely solve this, right? So we can, for instance, we could solve the whole thing based on the 2 parts here, and then use the extra 3 to do tests to make sure everything worked out correctly. So this is the general idea behind frames. Again, the difference between a frame and a truss is that in a frame, the loads can be on the members directly. It doesn't have to be at the joints, right? And so while we do this is we follow a similar approach as for the method of joints for trusses, where we take the whole thing apart, but now instead of doing member by member, then doing forces, we take it away where the pins are and represent those pins basically by a hinge, right? Because we don't know what the direction of that force would be. Unlike in the truss where we knew the direction of the force, right? So that's kind of difference. And so next, what we're going to do is we're going to go through an example, one for a collapsible and one for a non-collapsible, but that's going to be the next video.